بسم الله الرحمن الرحیم. ضمن عرض سلام خدمت کاران برادران عزیز. امروز جلسه 17 درس زمین آمار هست، البته حضوری. چندین جلسه هم قبل از تعطیلات نوروز هم بعد از تعطیلات نوروز به صورت مجازی داشتیم و امروز هم جلسه روز شنبه هست، 21 خرداد ماه 1401. Today I would like to address this question given a single partial realization of a random function, and then we are asked to estimate the attribute under consideration over the block B indexed at S0. What do I mean by saying estimated value of Y over block B indexed at S0? If this is your study area, and then you do have a number of measurements in your study area, what do we mean by saying estimate the attribute under consideration over block B indexed at S0? Imagine that you would like to address this question. On the same study area, you are given raster-based data, remotely sensed data, satellite data. Which means, if this is your study area, then you discretize the study area into a number of pixels, and then you would like to compare and contrast ground-based measurement with air-based measurement. The basic question is this: how could it be possible to compare and contrast air-based measurement with ground-based measurement? The support size for ground-based measurement is point. The support size for air-based measurement is pixel. How could it be possible? When it comes to raster-based data, you do have pixel value at the center of each pixel. You have data emerging from satellite or radar at the center of this vision. And then, even it may happen that you would like to calibrate your air-based measurements, because when it comes to air-based measurement, you really do not monitor the attribute under consideration, but voltage or some other aspect of electronic instruments arranged to monitor remotely sensed data. And then you have to calibrate your air-based measurements in order to secure that you are talking about the same attribute. This question can be translated to trying to convert the support size for ground-based measurement. Trying to convert your point-wise measurement to block-wise measurement. That is what we are really after. That is a typical block. and estimate the attribute under consideration over block V index at S0. Of course, the name of this block is very different from the name of this block. You could call this S0 and then this S0 is very generic. S0 could be this block, could be this block, could be this block, and could be this block. You could either write down S0 here, or S0 here, or somewhere else. It really doesn't matter. But you have to differentiate between various blocks. Is it clear?
S0 is a point. یه نقطه است در واقع بلوک B هر جایی این داشته میتونه باشه.
This point is very generic. You could change this to this. Say this is S0. I'm just trying to differentiate between various blocks. The pixel value or the estimated value of Vy over block V index at S0 could be different for various blocks. As soon as you have ground-based measurement converted to pixel value, then you could compare and contrast your air-based measurement with ground-based measurement. Even you could start to correct your air-based measurement. What do I mean by correcting air-based measurement? You know for sure that you have to consider a trade-off between ground-based measurement and air-based measurement when it comes to accuracy. Your ground-based measurement is quite more accurate compared to air-based measurement. But the beauty of air-based measurement is that you could even have air-based measurement over water bodies, where you cannot put ground-based instruments, or Caspian Sea or Persian Gulf. Up to now, we try to have three concepts. What are those concepts? Known, versus unknown mean, and it really doesn't matter whether your mean is constant or variable when it comes to known versus unknown mean. The second concept, constant versus variable mean, and then the third concept, constant versus variable variance. You did realize that if we combine these three concepts all together, 8 scenario will emerge. And we managed to solve this problem using these 8 scenarios. Of course, there is no V here for those 8 scenarios. Today, we would like to add another concept, so-called D, point versus block estimation. Please pay attention. Let me underline this estimation here to emphasize the point that we could even have point versus block observation. Another concept could be put here. Point versus block observation. But for the time being, for this concept, this fourth concept here, I will assume that my observation is pointwise. Therefore, if you add this to your other scenario altogether, you are going to have 16 scenarios. The very first one could be known and constant mean, constant variance, block estimation, because we have already addressed point estimation. The second possibility, or I would say the 10th possibility or scenario, could be unknown mean, constant variance, constant mean, constant variance, block estimation. We will call the 9th scenario block simple kriging, the 10th scenario block ordinary kriging, and so on. Altogether 8 scenarios. And if you add this 8 scenario to your previous 8 scenario, altogether you are going to have 16 scenarios to solve this problem. I hope you appreciate the point that when we raise this question, it is quite important to clearly document your assumption. The 8 new scenarios are different from one another because the assumptions are very different. What I'm going to address today, I'm not going to address 8 scenarios. I will leave 7 scenarios to you in case you are quite curious to see how we would structure your block kriging for other scenarios. Today I will try to address these scenarios. Constant, and unknown, mean, constant variance, and block estimation. When your mean is constant, when your variance is constant, that means the parent random function is stationary. Which means you do have access to both covariance function and the variable function. If I replace this block to point estimation, can you tell me the kriging system either in terms of covariance function or variable function? Therefore, in order to solve this problem, what I'm going to do is to write down the kriging system for this system and this block is point. And then see what will happen if we change this point to block estimation. Summation I j from 1 to n lambda j r sub si sj plus r sub S0 SR. Please pay attention that both lambda j and mu will be a function of S0. If you change S0, then these vector lambda and this scalar quantity mu will change. I have to tell you that I has to go from 1 to and then here I has to go from 1 to n lambda I, which is a function of S0. This is your Kriging system in terms of covariance function. For the case when your mean is constant and unknown, your variance is constant and your estimation is pointwise. You could write your Kriging system in terms of variogram as well. You might be quite curious to see what would be your Kriging system when you change block estimation to point estimation to block estimation. Please pay attention here. This covariance function or this variogram function could be considered to be for y or w, because covariance for y is the same as covariance for w. This covariance or this variogram is called point-to-point covariance. Point-to-point variogram. Point-to-point covariance, point-to-point variogram. You can expect, you can anticipate that your Kriging system for this case would not change the left-hand side, because this has nothing to do with block. This is point-to-point, and this is INSJ, is point-to-point covariance function for your observation, and this is point-to-point variogram for your observation. But when it comes to this S0, because this S0 is no longer a point, but a block, you would anticipate that your covariance function here and variogram function here will become point to block. And we have to figure out the structure of this point to block estimation, point to block covariance, point to block variogram. If you are in a deterministic world, please pay attention. If you are in deterministic world and you do know the closed form function for the attribute under consideration over 1D, 2D, or 3D, how you would proceed to compute the mean? What do I mean? If you have a function in 1D or if you have a function in 2D. If you have a function in 3D. And when it comes to this one, x can change between A and B. If here you have a 2D function, x could change between y could change between C and D. And then if you have a 3D problem, x could change between A and B, y could change between B and C, and Z could change between if you are given these three functions, and then you are asked to estimate the mean value of f over this interval, or the mean value of f over this interval, or the mean value of f over this interval, how you would proceed. That is a typical problem in engineering, mathematics, or even mathematics 1 or 2. When you are here, you would say the mean value of f can be written as this. That is how to compute the mean value of f over interval a from b. If you are in 2D, and then you are asked to estimate the mean value of f over this area, which is rectangular, then you would say the mean value of f over this area is C to D, A to B, dx dy. That is how to compute the mean value. By the way, here your computational domain is this. If this is your x-axis, then your interval is from here to here, a 1D problem. If you are in 2D, then you have to consider x and y. And from here to here is your variation of x. From here to here is your variation of y. And you are talking about mean value of f over this interval. If the, yes, I thought C is greater than D, D minus C. Here you are talking about mean value of f over this interval. Here you are talking about mean value of f over this interval, this surface area. And then if you are here, you are talking about mean value of f over b minus a, d minus c, f minus e. And this should go from E to F, C to D, A to B, f sub x, y, z, dx, dy, dz. If you do know the closed form function for variation of attribute under consideration, then you could find the mean value using these formulas. Please pay attention, this f here could be our y. You could replace this f with y, but because this y will be interacting with this y as a special coordinate here, I change it to f. The unfortunate part of the story is that in real life we do not have access to this closed form function. In real life we have only one single partial realization of our random function. Therefore, in real life, this integral will be replaced with summation. It will become one over m, and m is the number of data points within the interval, and this has to go from 1 to m f x xk. You will observe the attribute under consideration at a number of points within that interval, and then if you want to find the average, what you are going to do is to take arithmetic mean of your observation. If you are having a problem in 1D, if you have a problem in 2D, again you have to discretize your study area into number of points, observe the attribute under consideration at those points, and then tell k from 1 to m f sub x k y k. This is how to compute your mean if you have a chance to observe the attribute under consideration in your computational domain, your study area. And if you are a 3D problem, again you have to consider a few voxels instead of pixels. Monitor the attribute under consideration at the center of each voxel, and then use this formula to come up with the mean value. Now, if you want to solve this problem using this concept, what you need to do is to discretize your study area under consideration. Here you would like to have an estimation over velocity. Therefore, what you need to do is to discretize your study area into a number of points. Estimate the attribute under consideration at this cross red point, and then take their average. Therefore, if you want to solve this problem using traditional approach, you are going to have this estimated value of y over velocity v, index at S0 can be written as 1 over m. M is the number of discretized point inside your block. And then summation k from 1 to m y s prime of k. And these are the estimated value of y at each point. Please pay attention from very beginning of this course up to now. We have to differentiate between lowercase letter and uppercase letter, capital letter. If I use lowercase letter here, I have to use lowercase letter here. But if I use uppercase or capital letter here, I have to use capital letter here. As in geostatistics, our framework is stochastic. We will denote the attribute under consideration in capital letter instead of lowercase letter. And then you could say estimated value of y over velocity v index at S0 could be written as 1 over m, this summation. And then you can replace this with your point estimation. And your point estimation is this. Summation I from 1 to n, lambda I. This lambda I will be a function of S prime of k. And then observe value of y at SR. This is ordinary creation, by the way. If I ask Mrs. Rajabzadeh how many times I have to implement this relation to come up with estimated value of y over log v index at S0, what would be your answer? N times. Because this k should go from 1 to n. At first, you have to estimate y at S prime 1, which is this point here. And then you have to repeat this for y at S prime 2. Please pay attention. I try to differentiate between my observation and my discretization point by putting a prime on top of S. This prime on top of S implies that I'm talking about discretized point inside each block. It means if I want to stick to tradition, to what I know in advance, what I need to do is to repeat ordinary Kriging n times, and n is the number of discretized points inside each block. And then use this relationship to come up with estimated value of y over block v index at S. Question: would it be possible to eliminate this n-time computation of Kriging system and try to cast my Kriging system only once? Let me repeat the question again. By now, you appreciate that if I want to estimate y, I have to repeat ordinary Kriging n times, because I have n points, and I have to estimate the attribute under consideration at each point, which means that I have to repeat the ordinary Kriging system n times, and then take an average. I do have a criticism, and I have to be quite honest with you with this criticism, and I would like to invite you to see how you would address this question. address in literature. Under what condition I can assume that if I take the average of these points, then it will become y hat or log v and it's exactly zero. And you do know when I address properties of kriging. Remember that I told you that when you start to differentiate between your left and right hand at that time, you were told that if you are given a series of numbers and then you are asked to find a representative, you will say their average is going to be their representative. And we show in this course that if the numbers are purely random, then their representative is going to be their arithmetic mean. Here, in almost every textbook written on block kriging, they will assume that these points are purely random, which is not the case. These points are correlated with one another. Which means we have to find the mean of the series of data, assuming that they have correlation. Keep this criticism in mind to see how you can tackle this problem when you read a number of textbooks on block kriging. But for the time being, you have to have this criticism in mind that it is assumed that you have purely random numbers here, and you will try to find the arithmetic mean, and then you call that arithmetic mean to be estimated value of y over block v index at b. Now, let me repeat the original question again. As you realize, I have to repeat kriging system for point kriging, ordinary point kriging m times. Could it be possible to eliminate this repeated computation of ordinary kriging and write the block kriging system only once? Let me put these things in 9 or 10 steps that we have in previous lectures. Step 1. In step 1, we have to switch from y to w if you are given m. Because you are not given m, therefore this step is not applicable. Step 2. I'm talking about the same scenario, but instead of repeating ordinary kriging m times, I would like to cast my kriging system for block kriging only once. Step 2. Estimated value of y over block v index at S0 could be written as a linear combination of observation. Please pay attention. This formula is very different from this formula. And you can see even by just looking at each formula. Here, my lambda could be qualified by putting block kriging. But these lambda here are not block creating. These are point creating. That is how we are going to cast our creating system for block creating only once. Here, your lambda is point creating, point ordinary creating. Here, your lambda is block creating. And we have to see how it could be possible to come up with lambda for block. Step 3. You have to cast your residual. Here, your residual should be qualified by saying residual over block V index at S0. And this residual can be defined as estimated value of Y over block V index at S0 minus true value of Y over block V index at S0. Of course. See, if I remove this hat here, if I remove this hat here, it will become true value of Y over block V index at S0, and it can be written as 1 over M, summation from 1 to M, true value of Y at each point. True value over block can be connected to true value at point. Therefore, if you want to know what is this true value of Y over block V index at S0 can be written as 1 over M summation K from 1 to M true value of Y at each point. Okay? Residual over block V index at S0 can be written as estimated value of Y over block V index at S0 minus true value of Y over block V index at S0. And by true value, I mean this. Step 4. You have to impose unbiasedness condition on your residual and see under what condition your expected value of residual is 0. Expected value of residual over block V index at S0 under what condition will become 0. Please pay attention. I put a question mark on top of equal sign to tell you that I have to explore under what condition this expectation is 0. It may happen that it is automatically 0 with no condition, or under some condition it will become 0. this operator is a linear operator, I can bring this expectation inside and write it as summation I from 1 to n lambda I bk, which is the function of your block index at S0, and then expected value of y at SR. Minus 1 over n k from 1 to n expected value of y at S prime k. By the way, it seems that I have to change this into, let me see. Now, here it's okay when I'm here, but no, there is no, because I did not open any sign like that, so that I have to close it. Now, you are told that your mean is, what? Your mean is constant. Constant and unknown mean. Because your m is independent of spatial location, you have to replace this with m. Okay? And because m is independent of index of summation, you can bring it outside. Now, look at this one. What would be the expected value of y at S prime k? M. M. Because these points are not very different from model points. And the expected value of any point under consideration, it really doesn't matter whether they are observation or true value. This will become M. M lowercase letter. And because this M has nothing to do with index of summation, you can bring it outside. And then you have summation from 1 to M, 1. Yeah. It will become M. That M will cancel out with that M, and it will become minus M. You can factor out this M. Now Mrs. Zara has a chance to utilize the unknown property of M. Because M is not given, M is not known, therefore you want to have expected value of residual to be 0, under what condition your residual will become 0? Because M cannot be 0, therefore this part has to be 0. For residual, for expected value of residual to be 0. Therefore, if you put this equal to 0, M cannot be 0 because you have no idea of M. Therefore, this term inside the bracket has to be 0. Please pay attention. These are lambda bk. Therefore, the final output emerging from step 4 is to have this relationship between coefficient in order to honor unbiasedness condition. Now, step 5. When it comes to step 5, in step 5 you have to compute variance of residue. I replace estimated value of y or velocity v index at S0 with this linear combination, which we do have it in step 2. And as Mrs. Rajab was raised that question, I replace the true value of y or velocity v index at S0 with this counterval 1 over n this summation. And these are the true value of y at this discrete point. By now, you have to be an expert. Of course. By now, you are an expert in how to compute variance of this, and then 2 times variance of this and this. When you want to compute the variance of this linear combination, you have to ask yourself, am I okay to express it in terms of covariance of y? If your parent random function is stationary, then you are okay to write it down in terms of covariance of y. Okay? Therefore, the very first term will become double summation. That is variance of the first term. And now Mr. Iliati would like to tell us what would be the variance of the second term. What you need to do is to bring this inside, and then this is a linear combination, just like this. Instead of lambda, you have 1 over n. Therefore, it will become double summation k from 1 to n, summation L from 1 to m, and then 1 over m times 1 over m. 1 over m squared. and then R S prime K S prime L. That's how to compute variance of linear combination. Minus 1 over m 2 times 1 over m summation now here instead of writing it in this way, I would like to have this y over block B indexed at S0, the original part here, and then if you multiply this by this, it will become minus 2 summation I from 1 to n lambda I times covariance of y at Si y S0. If you have this y at S0 without this y be here, you would say minus 2 times summation I from 1 to n lambda I r of y Si y at S0. But here, if you have block true value, you will put it here. What I'm going to do is to compute this covariance separately and then plug it here. You may raise this question, why did you not follow this case? It is possible to follow this case, but you will realize that if you replace this with this and then try to compute covariance of this random variable and this random variable separately, then you will grasp it more clearly compared to this one. Therefore, let me compute covariance of y at Si, y b S0. Back to basic statistics. If you want to compute covariance between these two random variables, you can use this formula. Expected value of y at S0 Si times y over block B indexed at S0 minus expected value of y at Si times expected value of y over block B indexed at S0. That is how to compute covariance between two random variables. This is a random variable, this is another random variable, and that is how to compute the covariance between these two random variables. Now, we could replace this with this part here. Let me see if I have to change this to another notation. Y at Si times 1 over m summation k from 1 to m y at s prime of k. Just I replace this with its counterpart. Minus expected value of y at si, expected value of 1 over m summation go from 1 to m y s prime k. Because of the linear property of this operator here, I can factor out this 1 over m summation call from 1 to m from this and this, because this is coming in both terms. Therefore, 1 over m summation call from 1 to m. I factor out this because it's coming in both terms, and then I can write this expected value of minus expected value of y at si, expected value of y at s prime of k. What I did, I just factor out this 1 over m summation k from 1 to m because of linear property of expectation. Now I can replace with it with covariance of s prime k, s prime s bar. Therefore, 1 over m summation k from 1 to m cos of s prime k s bar. Can you interpret this for me? Of course, no doubt, this covariance is point-to-point covariance, no doubt. And no doubt, you have to define I externally because K is not defined internally, I is not defined internally. Look at my original diagram. If you take a typical I like I equal to 1, for I equal to 1, you have to compute these covariances. Covariance between S1 and every point inside your block. And then add them together, divide them by m. And then go to the next point, S2. Again, connect. Find the point-to-point covariance between your second observation and every point inside your block and find the average. You would like to call this average for each point to be, you may want to call this R bar S prime K SI. just because of you have to change S prime from 1 to M, find the point-to-point covariance between every point inside your block and SI, and then divide this summation by M to find the average covariance between observation point and S prime K. Therefore, if you connect this part here to what I have here, all I need to do is to replace this covariance with this one. Therefore, variance of residual over block V index at S0 can be written as I from 1 to N, J from 1 to N, lambda I, lambda J, R sub Si, Sj, this is the first term, plus 1 over M square, summation K from 1 to M, summation L from 1 to M, R sub S prime K, S prime L, and then when it comes to the third term, minus 2 times I from 1 to N, lambda I, R sub S prime K, S I. You may want to write down the original term here. Instead of writing the average value of R, you could write this one, 1 over M times this. Let me put it here in order to emphasize that if you ask me what happened to this K here, I would say I have to write down I from 1 to N, summation K from 1 to M, lambda I, and this lambda I, by the way, are VK, and then R sub S prime K, S R. Okay? I have two choices, whether write the average value or write the original results. That is a step. This is 5 or 6. And now I have to switch to step 6 or 7. 6. Step 6. In step 6, I have to cast my objective function. If you call this f sub lambda, then in step 6, your final objective function has to be unconstrained. Here, your objective function is constant. Let me write it in qualitative term, minimize f sub lambda subject to unbiasness condition. This is a typical optimization problem where the objective function is subjected to an equality constraint. If you want to solve this problem for lambda, you have to first cast your objective function so that it is no longer constraint. And this is Lagrange multiplier. That is how to cast your objective function so that it is no longer constant. Now, when it comes to step 7, in step 7 you have to minimize this G. Here you have n plus 1 equation with n plus 1 unknown. What I am going to do is to take partial derivative of g with respect to lambda I, divide both sides by 2, and then put the known on one side and unknown on the other side. As you can see, J is defined internally. You have to define I externally. Remember that when I was interpreting this formula, I told you what, Mrs. Rajabzadeh. Here, I told you if you want to compute estimated value of y over block B index at the 0, you have to repeat the ordinary Kriging system n times. But with this formulation, you can only use Kriging system one time. And the minor change here has something to do with this here. If you compare this Kriging system, which is for block Kriging, with its counterpart point Kriging, everything is the same except here you have S0, Si. But when it comes to block Kriging, this is point to block coordinates. 1 over m times this summation. And if you put I equal to 1, that will give you the average point to block covariance for observation number 1. If you put I equal to 2, that will give you the point to block covariance between observation number 2 and your block. If you are asked to estimate the average precipitation, say, over Fars province, this is the boundary of your Fars province, and you have 163 rain gauge stations in your Fars province. In that case, your block will become as large as the study, only one block. What you need to do is to discretize your study area into a number of points and try to compute the average variance, point to block covariance for every observational point, and then use this equation to come up with this coefficient. And as soon as you have this coefficient, you could test the linear combination of observation to come up with the average value of precipitation over Fars province. Could it be possible to write down the kriging system in terms of variogram? Because the current random function is stationary, we could tell R plus gamma is equal to sigma 2 because sigma 2 is constant as well. Therefore, if we replace this with sigma 2 minus gamma, this sigma 2 will become outside and will be cancelled out with this sigma 2 here. And the result will become, let me write it here. Mr. Ahmed, are you with me? Okay. Minus and that's going to be kriging system in terms of variogram for blockage. Of course, block for linear kriging. That is step 7. Step 7. Both of them are the same. And then when it comes to step 8, you have to solve this system for lambda and mu. That is step 8. You have to solve this system for lambda and mu. And then when it comes to step 9, you have to compute or answer the original question. Estimated value of y over block V indexed at S0. By the way, these are block estimates. S0 can be written as a linear combination of observation. Now, when it comes to step 10, you have to go for computation of variance. And as Mrs. Zaren know, we have 3 variants to compute. variance of estimated value, variance of true value, and variance of residual. Let me start with variance of true value. And Mr. Zairi would like to tell us what would be the numerical value of y over velocity v indexed at S0. Not over the look, but at the point. Variance is constant, independent of spatial location for a point in your study. How could it be possible to compute variance of true value? It will become variance of 1 over m k from 1 to m, true value of y at s prime k. And this is a linear combination. 1 over m square double summation k from 1 to m summation l from 1 to m r sub s prime k s prime l. Okay? That's going to be variance of true value for y over velocity v indexed at S0. When it comes to variance of estimated value of y over velocity v indexed at S0, you have to replace this with this summation and find the variance of this linear combination. It will become a double summation. I from 1 to n, j from 1 to n, lambda I bk, lambda j bk, r sub si sj. And you can simplify this. How? You can multiply both sides of this equation by lambda I, take summation from I equal to 1 half to n, and then replace this double summation with what remaining. One over m summation k from 1 to m summation I from 1 to n lambda I, which is for bk, times r s prime k s r minus mu. That's going to be variance of residual, variance of estimated value of y over velocity v indexed at S0. And then you have variance of residual. Over velocity v indexed at S0. Again, that is your variance of residual. You can replace that double summation with this one and then simplify it with what is remaining. We can replace that summation with 1 over m lambda I dk r sub s prime k si. This is how to replace this double summation to this one, and then plus 1 over m square double summation I from, from 1 to m, summation L from 1 to m, R sub S prime K, S prime L, minus 2 divided by m, I use this one, summation K from 1 to m, I from 1 to n, lambda I, which is bk, r sub s prime k s I. As you can see, this will be simplified with this one. What happened to mu? I have to put minus mu here. Why? Because if you replace this double summation, you have two terms. This is the first term, and minus mu is here. Okay? Now, how would it be possible to simplify this? We have 1 over m here, and we have 2 divided by m here. Therefore, this and this will become one of them with minus sign. And then we have this, therefore, let me write it here. Mr. Ahmadi, are you with me?
Yes.
1 over m square, summation k from 1 to m, L from 1 to m, R sub S prime K, S prime L, minus mu plus 1 over m from 1 to m, I from 1 to n, lambda I bk, r sub s prime s I. Variance of residual in terms of covariance function. Mrs. Rakabzadeh, could it be possible to write down this in terms of value? Let me write it here and raise a question for you. Variance of residual over below V indexed at S0. You could write this as sigma R, this R stands for residual, and then BOK, and then raise it to the power of 2 to become variance. Variance of residual for Bloch ordinary caging is equal to Now, you do know that R for SI, Sj plus gamma SI, Sj is equal to sigma square. And this sigma square is the global variance. Now, you would like to replace this R with that one. It will become 1 over m square summation k from 1 to m L from 1 to m, and then you would like to replace that one with S prime K, S prime L. This is how to replace R with gamma. Minus mu minus 1 over m summation from 1 to m I from 1 to n lambda I sigma square minus gamma S prime K S R. Look at the first step. Can you tell me what happened, Mrs. Lawrence, for the first step? Double summation sigma 2.
Summation term.
Because this sigma has nothing to do with index of summation, you can bring it outside. And then you have 1. This first summation will give you what? Summation L from 1 to n, 1. It will become m. And then this m has nothing to do with index of summation, you can bring it outside. And this summation will become m times m2. And m2 will cancel out with this m2 here. Therefore, this part is sigma 2 minus 1 over m square summation from 1 to m summation L from 1 to m gamma S prime K S prime L. Minus mu. And now, when it comes to this one, could it be possible to help me with this first term? Because this sigma 2 has nothing to do with index of summation, you can bring it outside. And then this summation, I from 1 to n, lambda I is equal to 1. Therefore, this will become n will cancel out with this m here, it will become minus sigma 2. And then this minus times this minus will become positive. Now, if you simplify this, it will become 1 over m summation Ka from 1 to m, I from 1 to n, lambda I bk, gamma s prime k si minus mu plus 1 over n square Ka from 1 to m summation L from 1 to m gamma s prime k s prime k. Now I would like to invite you to tell me the answer to this question. This question has nothing to do with what I have over the board, but it is connected to what I have. I shared the similar session from previous semester with you through WhatsApp. There is a mistake toward the end of my derivation. Look at the session again and tell me what the problem is, what the mistake is. جلسه بلوک کریتینگ ترم قبل آخراش نمیدونم به چه دلیلی یک اشتباهی صورت گرفته. Today I try to correct that mistake. Try to delineate that mistake in my previous lecture on block creating to see what was the mistake and how I try to correct that mistake in this lecture. That is it. Step 10. And we are done with block creating additional computation regarding computation of variance of true value, variance of estimated value, and variance of residual. از حوصله همگی سپاسگزار هستم. تا روز دوشنبه همگی رو خدا بسپارم. ما روز